Right, so we're recording now. So good evening, everybody, and welcome to tonight's session. So tonight we're going to look at Unit 8, Mechanical Principles, and we're looking at Assignment 3 still. And this is the second part in Assignment 3. So on Tuesday we did part 1 of Assignment 3, so we'll do part 2 this time. So what we're going to do, first of all, we look at the assessment criteria. You should always have a look at the assessment criteria just to make sure that you've met all the requirements of the criteria when you've answered your questions. So when you've finished, have a quick look at the criteria just to make sure that you haven't missed anything out. So we're going to look at P8, which is a pass criteria. So we're going to explain the conditions required for constant velocity ratio between two joined shafts. So we look at different types of coupling, and we look at the assignments and how you should approach that assignment. Then we're going to look at the merit assessment criteria, and we're going to examine devices which function to store mechanical energy in their operation. So we'll look at a few possible contenders for that application, and we'll discuss them. And the last one, which is the D3, and we're going to examine the cause of a documented case of mechanical power transmission failure. Yeah, and the steps taken to correct that problem, and whether there was any sort of rectification issues or changes to the design as a result of the analysis. So it's broken down into 3 tasks. So the first activity that addresses task 3. So we'll do task 3 first. Then we've got activity 2, which looks at the M3 component. And then we've got D3, the distinction criteria, and that's covered by task 5. So that's what we're going to do tonight. So hopefully we'll make some progress. And when you're finished, if you can ask me any questions if you have, so we can make sure that you're going in the right direction with the assignment. So in this presentation, the way I'm going to approach it is we're not going to do an example tonight because the type of questions don't sort of lend themselves to doing examples. So first of all, we review power transmission and shaft coupling techniques. So that will address task 3. We're then going to discuss energy storage techniques and the principles involved. That's task 4. And then we're going to provide you with some direction and approach to answer task 5. Right, so first of all, this is the question on task 3. So I'll go through the question. So what we have, explain a method whereby torque can be transmitted between 2 non-axial shafts. All right, so just bear that question in mind, and we'll look at the answers to that question in a bit. So then we're going to look at what's the basic problem with a simple universal coupling and how can it be solved. And there is a serious problem with universal couplings, but it's solvable. That's the main thing. And then we're going to look at what conditions are needed to create for a constant velocity ratio between 2 joined non-axial shafts. So it's the solution to the universal coupling problem. That's what we're going to look at in part C. So on this image, we've got a few universal couplings. So we've got close coupled couplings. So there's some flexibility in that you've got a rubber donut shape between the 2 flanges of both ends of the shaft. So it provides some flexibility between the drive shaft and the driven end of that shaft system. Likewise with this device here, so let's put the pointer on so we can see it a bit better. So this is another close coupling. Again, they have limited amounts of flexibility. They can only cope with a limited amount of misalignment. So they're not really flexible couplings, but they do allow for misalignment of the shafting systems. So they're referred to as close coupling systems. We then have what we call the universal coupling system, and you'll notice that it has two ends, and that's quite common with universal coupling systems. I will explain why when we get towards the end, why you need the two ends and have universal couplings at both ends of the shaft system. So let's look at the type of couplings. So first of all, we've got close couple power transmission couplings. So we've got the example here. So they can be offset misaligned. You can have angular misalignment, but the type of coupling you use with them is generally very limited to the amount of displacement it can actually cope with. Now, all systems will have some sort of misalignment in. So for instance, say this end was a motor. So you had a motor at this end and it was driving a pump at the other end. Now, quite often what happens is that when you start a pump, a motor system, what will happen is the pump will warm up and its position will move relative to the motor. So it can be misaligned to start with, and the alignments could actually improve. Or the other way, of course, the alignment could become worse because thermal growth in maybe the pump, because of it's pumping a hot fluid, it can move the position of the bearings and you get some misalignments. So you're always going to incur some sort of misalignment in most shaft systems that join probably a motor and some sort of pumping systems. It's very common to have a degree of misalignment. Now, quite often you'll see these are coupled together with just bolts. So they're pulled together so that they actually tight together. And the reason that is usually because the relative movement of the two shafts is so small, and the bearings within that pumping system and motor system can deal with that misalignment. But it's not always the case. So that's why we use close coupling, close couple power transmission couplings to allow for this misalignment. It has an additional benefit as well, is the couplings can stop torsional vibration transmission from maybe a motor or a compressor to a motor or vice versa. So it can arrest, excuse me, torsional vibration. So they have a twofold application. The other flexible power transmission coupling we're going to look at is one that is used to deliver power from a drive. So this one shows a tractor driving some sort of machine. And what we have a universal coupling at one end, excuse me, and we have a universal coupling at the other end. Now, there's a good reason for that, and I'll explain what that is in a moment. So if you look at this system, it's transferring power from the drive, from the tractor to the machine, and a rotational power. And we also have to make sure that we don't have an issue with the rotational velocity of the output. Meanwhile, this device is going to move up and down. So it's very similar to a car suspension, isn't it? It can move up and down. But again, we've got to make sure that we get a constant velocity to the driven item. So what I want you to do when you have a moment is to look at this video. So there's a link to this video in the notes. I'm not going to start it now because it lasts about 7 minutes. So what you can do when you have a few minutes, have a look at this video and it will explain the issues we have with universal couplings. So this answers question B. What is the basic problem with simple universal couplings and how can it be solved? Now, first of all, before you solve a problem, you've got to understand the problem. So the problem with the universal coupling is if you have a steady rotational velocity at the input, what you'll find is that the output shaft, although it rotates, it doesn't rotate with constant velocity. It tends to sort of go up and go down around the mean velocity. And this video demonstrates that very clearly, but there is a solution. So the solution, you'll see that in the video, and that's the sort of basis for part C, which asks what conditions need to be created for a constant velocity ratio between two joined non-axial shafts. So again, we'll come back to the universal coupling. And if you've watched the video, what that would show you is that if you have a universal coupling and another universal coupling joined by a shaft, first of all, you've got to bear in mind that universal coupling is there to allow this one end or the other to move up and down. So this could move up and down. Let's put a pen on there. So one end or the other can actually move up, or it can move down. Yeah. So that means the length change, and quite often you'll see there's a section in the middle allowing the length of the shaft, driven shaft between the two couplings to become shorter or longer. The main thing to note is that these end flanges will be parallel to each other. So the key to make sure that you get a constant velocity ratio between the inlet shaft, between the inlet there and the outlet possibly, is that the angle beta 1 must be the same as beta 2. And when you've watched the video, you'll understand why, and it's a good demonstration. I'm not going to tell you the answer. I want you to find that out for yourselves. So you can see the same principle applies to a motor car. So we've got a gearbox, we've got a propeller shaft going from the gearbox. Okay, there's a center support on this one. But what you will notice is the rear axle, again, that's going to move up and down as you go along, but it's going to move up and down in a vertical plane. It's not going to move backwards and forwards. It's just going to move up and down. So that means when this moves up or down, what will happen is that the angle between the upper line shaft and the angle of the propeller shaft will remain constant in all cases, regardless of where the actual differential, in this case, the position of the differential, as it moves up and down, as it goes over bumps. And that's very important to make sure that those two angles remain the same. And you'll see that. Please watch that video. It'll explain it, and it will give you the answer as to how to overcome the problem of variable speed or outputs from universal couplings power transmission systems. So I'll put a few more images there. Likewise, this image here shows that angle there between the input line shaft and the propeller shaft, and also the angle between the output shaft and the propeller shaft. And again, similar to the car, they have to be the same. There is an alternative, and you could have this sort of arrangement where you have, these are not actual shaft, they're not actual in the same direction. So, but providing that these two angles are the same, then it's going to solve the problem that you'll have a constant inlet velocity and you'll have a constant outlet rotational velocity. So that solves the problem as well. You do have to be careful though that these universal couplings are phased in the right direction. So if you get them out of phase, so perhaps this is more twisted round than that one. If they're out of phase with each other, then it'll give rise to massive vibration in the propeller shaft. And that will lead through into the driven shaft and to the driving shaft, and can cause gearbox failures, bearing failures, all sorts of issues. So phasing of the universal coupling is vitally important. Again, you'll see that from watching the video in trying to answer previous task 3 part B. Right, so I think we've said enough about that, about task 3. Now that should give you enough to really have a good stab at task 3. So task 4, so the question is research and discuss 2 devices, 1 mechanical. You can do 2 mechanical if you want, don't have to be 1 mechanical, with 2 mechanical, but you can always put an electrical system in, such as battery storage. That's up to you, but you can do 2 mechanicals which store energy. So your discussion, so we're sort of looking at a brief sort of section of discussion really, to focus on the principles of storage. How does it work? Its application, where's it used, and how it operates. Okay, so we'll talk a little bit about that now. So what we have a pump storage scheme. That's an energy storage device. Okay, it might be on a massive scale, but it's still an energy storage device. So the principles of operation is that you have an upper reservoir and you have a lower reservoir, and you've got a pipe joining the two. That's referred to as a penstock. And just before the water from the top reservoir enters the bottom reservoir, then you put a turbine, and that turbine will extract the energy from that fluid and drive a turbine generating electricity. The issue with pump storage is that there's only a limited quantity of water. So you can only operate these plants for relatively short periods of time. They're not continuous because you can't top the water in the upper reservoir quick enough to provide continuous power generation. And one of the issues is that the power from the turbine is a function of the turbine efficiency and the mass flow rate and the height h above the turbine. And it goes down the penstock. It'll lose some pressure, but it's limited normally to about 10% of the available pressure head. So you've got a certain pressure head, which is the height from the turbine to the surface of the upper reservoir. However, as you get fluid flowing down the pipe, you get pressure losses in the pipe. So the potential energy will have reduced slightly, and they aim to limit that to about 10%. So the energy comes from potential energy and the mass flow, the amount of quantity of water flowing. And of course, you've got the turbine efficiency to take into account. Typically, these are in excess of 80% efficiency. So you can have a stab if you've got a certain flow rate, you've got a certain potential energy, then you can have a stab at the power output of the particular turbine. Now, the problem with these turbines, as it's called, it's a pump storage scheme. So that means when the cost of energy is low, so overnight when the electricity price is low, whoever operates the plant will reverse the turbine so it operates as a pump. So it will pump the fluid or the water from the bottom reservoir to the top reservoir. Yep. Now, if you look at it, pump efficiency is quite low because primarily this is a turbine, produce as much energy as possible. So the consequence of that is the pump efficiency will be slightly lower. So whatever energy you get out from the turbine in letting the water flow down, you're going to use more energy to pump that water back up. So that's a serious disadvantage, isn't it? Now, if you look at websites and sort of literature associated from the people that run these plants, they claim that they're green energy. Well, I want you to be aware of and to think about that because it's anything but green. You know, it's the opposite actually, because that energy that you use to pump the water up, where does that come from? If it comes from wind turbines, then it is truly green. But if it comes from gas-fired power stations, then it's not green at all, is it? So you've got to think about that. But they will advertise these as green power stations, but they're not. They might be locally green, but there has to be probably more than likely will be emissions somewhere else in the country from a gas-fired power station. So think about that. It's green credentials. It's not always as what it looks like. So another energy storage is a flywheel. So a flywheel is simply a mass, a metallic mass with lots of weight in it, and it spins at high speed, usually in a vacuum, so it reduces the resistance, wind resistance. And what you do is when you've got cheap electricity, you'll spin that, you bring that up to speed. You'll also put some energy in the batteries, and the price of energy will go up, the electric price will go up, so they'll stop taking energy from the grid. But then the battery will try and keep this flywheel spinning until there's a demand for it, and then the energy will be released back into the grid. But the consequences is that the flywheel will slow down eventually. So there has to be some fairly sophisticated electronics to make sure that we keep the frequency within limits. I'm going to talk a little bit later on about when these units are actually employed and when they're put into action, into service. So here's another scheme, and there's some harebrained schemes around. So this is one, I've never seen it. I've only seen pictures of like this. So this is a spring energy storage. So spring energy stores potential energy. You squash a spring, and what happens is stores potential energy because it's got the potential to do work if you allow the spring to expand again. So what happens in this system is that you may have, again, low electricity prices. So you'd use a fluid to fill this space, compressing the springs, which might be on some sort of diaphragm, similar to an accumulator. Then you shut off the inlet valve, and when you need the power, you'd open the outlet valve and drive some sort of power generator. So the springs would release their energy and push this diaphragm up and push this fluid out of that vessel. And it's a bit unusual. I can't say I've actually seen a real one. Other potential energy storage schemes is what they call the gravity energy storage. And that relies on a mass down an old mine shaft generally. So you have a heavy mass. And what you do again is when the electricity price is low, you wind this mass up using an electric motor. Again, it's taking power from the grid. We don't know where that comes from, so it could be a combination of renewable energy and from fossil fuels. It'll raise that mass and keep it up the top until that energy is needed, and then it'd be released, and through the wiring system, it'll drive a generator and send that energy back to the grid, to top of the grid demands. So it's another sort of scheme, and these have been built, so they're not that they are unusual, but one or two have been built, so it has potential. One scheme that has been introduced in Northern Ireland is a compressed air storage scheme. Again, use a compressor, low energy prices at the time, overnight usually. So we use a compressor driven by a motor and compress air into a cavern below ground, which is a sealed cavern. So we increase the air pressure until such time that when the energy prices go up and the demand starts to increase rapidly, then you can let the air out of that cavern and put it through. This is called the recuperator. It could go straight through a turbine. But what this does, it drives a compressor, and that compressor has an air system, and you're able to use combustion or high pressure air or a gas, a different gas, and you can use that to drive a turbine and return that air, that fluid back into the recuperator or the compressor section. And the air is then just what air that you've actually allowed to expand is exhausted back into atmosphere. So again, it's not a green system by any means. They have built these in Northern Ireland. So you could actually Google that and see how it operates, maybe get some feedback on its performance. One last scheme, and whether we class this as a compressed generation and storage, and it's looking at a hydrogen plant. So you take renewable energy, and again, when the demand is low, so there's not much domestic or industrial demand for electricity, we can actually, and the wind's still going to blow, or the sun's shining, or we've got maybe some geothermal or hydro scheme where there's no demand for energy, we can use that energy. So we can use an electrolyzer to generate hydrogen, and we can put that into hydrogen storage. We can also use battery storage as well for energy storage. Now, what you can do with that hydrogen, you can actually allow that hydrogen, pass it through fuel cells, and that can be used then to generate electricity. We can also use the stored hydrogen by mixing it with CO2 in the bioreactor. And CO2 and hydrogen, that's the basic of methane, which is natural gas. So we can actually generate natural gas, which we can use for the national grid, a high pressure national grid system. So that can be used for fueling maybe lorries and vehicles that require high power, or we can use it for heating in the home, or we can actually generate it through combined cycle gas turbines and produce more electricity. So this has quite a lot of potential in my personal sort of opinion, but I'd like you to have your own opinions. So if you sort of want to have a look at that, put your own opinion on it. You know, don't take mine. Everybody has an opinion about these things of the way ahead, but it does look like it has some potential. The other point of this is what they call pyrolysis, and that's where you burn sort of wood where in a situation where there's no oxygen. And what that does, it creates hydrogen and gases which can actually be put into storage. So that's a system of generating hydrogen as well, using plant-based products. So it's another sort of arm to support the hydrogen potential. So right now what I want to do is, I don't know if you've ever had a look at this, but this is what they call a grid watch. So I'm going to see if I can go onto a live grid watch. I don't know if it'll work. So let me use the mouse. So I can't share that screen with you, can I? Anyway, we'll have a look at this one as it is. So what this is, this was taken about an hour ago. And what this gives you is tells you where our energy supplies come from. Now, if you look at this graph that I'm highlighting here now, so let me put the pen on. You'll see this gives a daily profile. And what happens is, this is around midnight here. And you can see as through the days, the power increases and you get a peak demand about 6 o'clock in the evening. And then overnight it drops off again. So you can see today, this is where we are, and this is about 5 o'clock. The power demand has been increasing slowly. And the reason you can tell the demand was increasing, if you look at the frequency is below 50. That tells you the demand is increasing. Because what's happened, as the demand increases, what happens is the generators around the UK will all slow down ever so slightly and the frequency will drop off. So what the National Grid do is they'll bring up some devices, some more generation. And the way they can do that is to use what we've just talked about, energy storage devices. So one of them we talked about was a pump storage. So you can see there's pump storage up here. And 5 o'clock, that was actually supplying about, was it 3.3% of the UK energy? But it's only for short term. And what they use the energy storage for is to try and regulate the frequency. So if the demand goes up, they can bring pump storage on quickly, or any of these storage systems that we've talked about. They can be brought online quickly to meet that demand and bring the frequency back onto 50 hertz until the load starts to taper off again. So once the load drops off, then they can knock off the energy storage devices, and they can then be recharged overnight, ready for the next peak. A typical example is given of a quick demand where these energy storage schemes are needed quickly, is where you have commercial breaks on a television. So there's a TV program on that everybody's interested in. There's a commercial break. People switch on the kettle, and what happens is that the demand shoots up and the grid frequency will drop off, and these sort of energy storage devices will be brought online very quickly to maintain a secure supply. So it's quite an interesting website to look at this. You can see where all that energy comes from. You can see our need at the moment is around just below 40 gigawatts. And what's interesting is from wind, 28% of our energy at 5 o'clock is coming from wind power. And we expect that to go up tomorrow. It's still about 28% now, actually. But what has gone up is the combined cycle gas turbines gone up to 30%. Because you can't just switch the wind on, can you? It is what it is. But you can increase the power through combined cycle. But it's a bit slower to react than the storage devices that we've just looked at. Right, let's move on to the next. Let's just finish that section off on task 4. So completing the assignment. So what we want you to do is discuss the energy storage and release principles. So how does it work? So again, we've discussed, that how the energy is stored by possibly pumping water uphill at night or spinning up a mass overnight. And then it's released as and when the energy is needed in a hurry. I want you to discuss when the energy is stored. So we're stored overnight, and when it's released and why is it released. So we just discussed that, and it's released to try and keep the frequency of the grid to meet by meeting the sudden increase in demand. And I also want you to pass a comment on what are the scheme's green credentials. Now, I did that with the first one, is that the green credentials were very poor for these energy storage schemes. It's worse than a combined cycle gas turbines scheme, unless we get all our energy from renewable sources. Something to bear in mind. Again, you can have your own opinion of that. And please, that's what we like to see. We want to see your opinion about things in this sort of assignment. Right, task 5. So we're sort of getting towards the end now. So task 5, I'll read the question. So by conducting your own research, so that's your own research, and you'll find this quite interesting actually, or by relating to your personal experience, I don't think many of us have that sort of personal experience. Describe a documented case of mechanical transmission failures. So you'll need to describe the mechanism involved in the failure, the consequence of failure, what steps were taken to correct the problem or the defect, and if any design modifications were required. Okay, so how are you going to address that? First thing to do is to look for reports and case studies about transmission failures. Now, there's a lot of them. They give case studies. The marine industry is quite good on propulsion shaft failures, train line accident investigations where perhaps the gearbox has failed and the train has derailed. So there's lots of them. So don't be sort of concerned. The only thing is with these reports, they're quite long because they have a legal requirement, so they go into lots of detail. So what we'd want you is to look at those reports and just pull the bare bones out of those reports in your particular situation. So suggested search phrases. So railway transmission failure reports is a good one. Marine propulsion failure reports is another good one that's going to give you failure of transmission systems. The train ones are very good actually because they talk about the accidents and what happened and how fast the train was going at the time, whether it's derailed, and there's quite a few of them. And one I read is the reason it failed is because they didn't put any oil in the gearbox. So so they had to change there was nothing wrong with the gearbox, so they had to change their procedures to make sure they checked the oil levels in the gearboxes. You would have thought they would do that anyway, wouldn't they? But anyway. That was one of the, maybe it was missed out. So the approach to looking at these reports is if you read the abstract or the summary, whatever it's called, and assess its suitability for your work. Is it something that you can use? Does it tell you what the cause of the failure was? Does it give details of the analysis, and does it give a solution to the problem? So again, in your report, I want you to report on the consequences of the failure, whether there was an accident, a fire, whatever the cause of the consequence were. Then detail the failure. So what happened? What was it? Some sort of fatigue failure, or was it an overload failure? And then the last thing is what steps were taken to correct the problem. So was it a redesign, or was it just to change operating procedures so that the failure wouldn't occur again? So that's what I want you to have a look at. That's the way you should try and report on task 5. Now keep it to no more than about 1,000 words. So, we don't want you to go over the top, and that's not an awful lot of words. It might sound like it, but when you read these reports, you'll probably find that about 50, 60 pages long. So you're summarizing that report into just a few pages at 1,000 words. So it's quite a challenge. So you've got to pick out the bare bones from that report. Okay, so hopefully that should point you in the right direction with addressing task 3, task 4, and task 5. One last thing on task 5. Don't forget the citations and referencing. That's more important than anything on this particular application. because you're taking information from a report. So you've got to say, include that report in the reference. And in the actual text that you're writing, you put a citation. The citation just says where you've got that information from. So it's fairly straightforward, but it's important, okay, because you are using information from another document, unless you're going to use your personal experience, of course. Right, so that brings us to the end of the session. So just to go over setting out the assignment again, contents page, we've done that before, haven't we? Identify each task either by letter or by number, so we know what task you're answering. Type up all written text. Equations can be handwritten, but make sure they're neat. Scan them in. Use your phone to scan them in if you want. A good way of scanning them in is use the phone and use Lens, Microsoft Lens. That's quite useful and easy to use. And then you can just email it to yourself. Use images. So especially in task 5, well, in all of them really, use images to help explain your answer, to support your answer. Yeah, but when you do use an image, give it a figure number and then write somewhere in the text as shown in figure 2 or as shown in figure 1 above. Anything like that to link your text to the image. Otherwise, the image has no purpose of being there. So you may as well not put it in. So please don't forget that approach. And as I've just mentioned, include accurate citations and referencing. Okay, so that brings us to the end of the section. So if you've got any questions, we'll stop recording. Here's my details. And if you've got any questions, hopefully we